have the second lecture by Eduardo Miranda. Please.
Can you hear me? Is it okay? Is it working?
Okay, I think so.
Is it working?
Yes.
Okay, good. Good morning, everyone, again. So, once again, here are where my notes are, okay? It's an evolving set of notes, so it's changed from Monday to today, so if you want to have a look at it again. I'm correcting typos and including some additional figures. And so, okay, so let's start by first sort of summarizing what we saw on Monday. So, very quickly, I talked about some of the basic models I'm going to keep repeating here. So the first is the Hubbard model, has a hopping term, an interaction term, and one of the interesting things about this model is that it has a metal-insulated transition at half filling, meaning when you have 1 electron per site, on average, there is a critical value of the interactions at which the system goes from a metal to a MOT insulator. I also talked about this very important single impurity Anderson model. This model is going to be the basis of what I'm going to talk about today. So it's a model of an impurity, which I call D, that hybridizes with one conduction band. The impurity has an energy epsilon D, and it's an interacting impurity. So what I talked about last time is that depending on the value of the interactions and of the other parameters, you might have a localized magnetic moment at the impurity or not, okay? And when you do have a magnetic moment, and you are at very low temperatures and energies, this model has no charge dynamics because the impurity is always singly occupied by 1 electron with spin up or down, but it does have spin dynamics. And the spin dynamics of the model is described by the Kondo problem, the Kondo model, which is this model here with the impurity now is a spin, just one spin, and interacting by exchange with the conducting electrons, okay? I also talked about the so-called spectral function of this impurity in the Anderson model, which is defined, I defined first the so-called Green's function of the model, and the imaginary part of this Green function gives you this spectral function. And I pointed out to you that, for instance, in this particular case, it's a symmetric spectral function, symmetric with respect to the frequency. There is a bump here at U over 2, U, the value of the interactions, corresponding to transitions where you go from single occupancy to double occupancy. If you look at the negative part, negative frequency part, there's also another bump where you go from single occupancy to 0 occupancy at minus epsilon D, or epsilon D. Epsilon D is usually negative. But most importantly for us is that at low energies, there is this resonance at 0 frequency, which to me here is the Fermi level of the problem. And this resonance, also called the Kondo resonance, it involves the physics of the Kondo, the low temperature, low energy physics of the Kondo model I showed before. And the spectral function in this case can be analyzed with what I call the Fermi liquid description of this spectral function. So in this case, the Green's function is simplified to this form here. You see that it has basically one parameter. This combination here, I told you, is very close to 0. When this is close to 0, if you take the imaginary part of this function, you get a Lorentzian, which is the form of this bump at omega equal to 0. The position of the bump is very close to 0. It's very close to the Fermi energy. This is what I call pinning of the Kondo resonance to the Fermi energy. That's one important fact. I'm going to come back to this later. And the other important fact is the presence of this Z quasi-particle weight parameter, which when you take the imaginary part, it's going to give you the width of the resonance. And this width, which, as I said, is given by z times this imaginary part of the hybridization. The hybridization is a property of the model. This is the definition of the hybridization function. V is part of the model. Epsilon k is the conduction electron dispersion. So this usually has a real part and an imaginary part. The imaginary parts times z gives the width of the resonance, and this is what we call the Kondo temperature. It has an analytic expression given there. This jk of the Kondo model can be related to u and epsilon d and v. I'm not going to show the formula here. But the important point is that this can be very small because of the exponential dependence, right? If j is very small, this can be very small. And it's a non-analytic dependence on jk. This is a non-perturbative phenomenon, okay? So the two important points here are the pinning condition, the pinning effect, the Kondo resonance stays at the Fermi level, and the appearance of this low energy scale, the Kondo temperature, which if you look at the spectral function, is the width of the spectral function, okay? We're going to come back to this during the rest of the lecture. Okay, so now, finally, I want to go from the impurity model to an approximate description of the lattice model. In this case, I'm going to focus on the Hubbard model, okay? So let me once again write the Hubbard Hamiltonian here. Okay, so a hopping term between sites and a local interaction term on each site, okay? So we want to solve this model somehow, okay? There's no exact solution in dimension higher than 1. There's no good analytical approach to this problem. There are numerical methods which have their own limitations. They are, you can't reach very large sizes. For some methods, you cannot reach very low temperatures. So everything is limited. You know, our understanding of this model is going to be limited by these problems. So what we are going to look at now is an approximate description of this model. It's a theory that came to be known as dynamical mean field theory, the MFT. It has been mentioned here before. It is an approximate theory. It's not exact, but it does have very nice features, and it does have a lot of predictive power, as I'm going to show you today. So what is the point of this approximation? This approximation is the following. Just like other mean field theories, for instance, of the Ising model, you look at a particular site of the lattice. Okay, so you have the full lattice here, and you focus your attention on a particular site. Now, this site, if you could look at it and measure it with perfect resolution and for all duration of time, it has a very complicated dynamics, okay? But what part of this dynamics of this local problem, the local site, is that it exchanges electrons with the rest of the lattice. If you just look at the site a long time, it's going to fluctuate between empty, single occupancy, double occupancy, single occupancy, empty, double occupancy, and so on. Electrons from the rest of the lattice will hop onto the site and hop off the site, and the occupation will fluctuate with time. Okay? This is what's pictured here in this schematic drawing here. Now, I want to make this very clear. The dynamics of the local site is not only exchange of electrons with the rest of the lattice. There are other phenomena that go on there. For instance, there is exchange interactions with the rest of the lattice, which are not described by this process of exchanging electrons hopping in and out of that site, okay? So from the point of view of what I'm going to show you here, I'm going to look only at this exchange of electrons from along the axis of time with the rest of the lattice. Okay, so the rest of the lattice acts as a reservoir of electrons for the single impurity. I'm going to call this an impurity, although of course it's not an impurity now. It's one of the sides of the lattice. Okay. Okay, good. But if I do that, let me not go there yet. So if I do that and I think about the single site, this is just like the Anderson's single impurity model that I showed before. Okay? This is just like the d orbital of the single impurity Anderson model I was just talking about a few minutes ago. Because in that model, what the d site does is it exchanges electrons with the conduction band. This is the term that governs that exchange process. So the electron can go in and out of the d site. The d site is interacting, has a U term, just like the Hubbard model, just like the particular site that I'm looking at has. Okay? The only thing is that I don't know what the band is in this case. I don't know what the V is in this case. But it does have the same dynamics as the single impurity Anderson model. Okay? So that's what this is going to be the sort of the starting point of the DMFT. Okay? So first of all, focus on a site. Let's say site 0. And describe it as a single impurity Anderson model. Now, the Anderson model, as I just said, is characterized by the V and by the conduction electron dispersion. Those two things combined can form this so-called hybridization function, which is defined over there. And all the information from the point of view of the site from the rest of the lattice is contained within this hybridization function. Okay? So if you look at the Green's function, I forgot to write the original expression that I wrote last time. The Green's function is given by this expression. So this guy is this guy, minus the self-energy, which takes into account the interactions of the lattice. If the interaction is 0, this is 0. But if not, this is the full Green's function. This is just, as I said, the Fermi-liquid parameterization of this guy here, which I talked about last time. So the information about the rest of the lattice is here. The information about local interactions is here. Okay? Good. So now, I can start by saying this. Take a certain hybridization. I don't know what that is yet, right? Because I don't know what these things should be for the description of this model. Solve the Anderson impurity model. What does this mean? What does it mean to solve the Anderson impurity model? So I've given you this, you have this, you have U. Solving it means finding the self-energy. Okay? So this is find the self-energy. How do you do that? Well, that's the hard part of the problem. Okay, that's, as I said last time, I'm not going to go into how to do that. I'm just telling you there are tools that do that for you. They are called impurity solvers. There are, I don't know, about 10 of them, each one with their own weaknesses and strengths. But I'm going to assume that somehow I can calculate this guy. Usually, I can do perturbation theory. This is perturbation theory. Okay, also. But usually, if you want to do a good job, for any value of u, you're going to do it numerically. Okay? So find this guy. There's more than perturbation theory. Actually, some of the results I'm going to show later are based on a mean field theory that's appropriate to this singular impurity Anderson model in the Fermi liquid phase. Okay? But that's for later. But somehow you can find this. Now the question is, okay, you did that, but I still don't know what that should be. Okay? So what's left to found here is self-consistency. So what I need now is self-consistency. In other words, I need to make contact with the lattice. I need to find a way of self-consistently determining what this should be. Okay? And that's what I'm going to describe to you right now. I'm going to tell you, and I'm going to appeal to physical intuition. I'm going to tell you how it's done. I'm not going to derive it. I'm just going to describe the process. Later on, I can tell you a little bit more about derivation. Okay? So what I'm going to do is the following. I can define what's called the Green's function of the conduction electrons, of the band, of the conduction electrons. Last time I gave the precise definition for the Green's function of the d orbital. Okay, but you can do the same thing. Let me put this here, actually. I'm going to put a C here because this is the conduction electrons. Okay? I'm going to define it in K space. It's a periodic system. K is a good quantum number. I can use the K basis to define this. And this is going to be minus I, just like before. Well, let me do it this way. T minus T prime. Then I'm going to do this. C, K, T, C, K, T prime. Angular brackets are averages with, statistical averages with the Boltzmann factor of the Hamiltonian. This is an anti-commutator because this is Fermi operators. And then this is factors there because this is a retarded Green's function. It's not very important for us right now to know where this comes from, but this is defined. And once it's defined, you can... Yes, please? Yeah.
Cosine somewhere?
Yeah, it should be hidden behind the minus sign.
Okay.
Can't you see it? See, not much space left there. Okay. Now, just like, now I can do a Fourier transform with this guy. Okay, so just like before, I think Leticia showed it here. This guy is actually dependent only on the difference and can do a Fourier transform on this t minus t prime, and you can write gk, gck of omega, and it's given by 1 over omega minus epsilon k minus, let's put a C here, a conduction electron self-energy now. So it's very similar to the other guy, okay? Once again, self-energies here are non-zero only if there are interactions. If interaction is 0, this is gone, and have a simpler form for the Green's function. Now, you notice here that this self-energy, which contains all the information about interactions, depends on K, okay? It depends, generally, this is completely rigorous for any lattice model, and it depends on K. So, the first approximation of DMFT. This guy only depends on frequency, okay? What this means is that this is a local self-energy. Why? Because if you do the Fourier transform of a quantity from k space to real space, and it has no k dependence, it becomes a delta function in real space. In other words, if you look at the real space propagator, or Green's function, it's the Green's function of one site with itself. So it's completely local. So this is a local approximation. Once again, just accept it, and I'll tell you a little bit more about this later. Okay, this is the first one. Now, you can do the following. Second thing, this guy is the same as this guy. Well, this is completely reasonable from the physical point of view because, okay, first of all, you need this first because it has to be local. You have to lose the k dependence. But once you lose the k dependence, it's reasonable that the correction, the self-energy, the interaction correction for the conduction electrons is the same as the local site because the local site is part of the lattice. So it's reasonable to do this. And third, finally, is you equate GC 0 in space to G, what I call D of omega. This is the local Green's function, the same thing that I said before. This is the Green's function of where you create a C electron on site 0, and you create it here, and you destroy it in the same site 0. So, just a second. So this is, in real space, would be the difference between sites. I'm telling you, this is 0. In other words, you start at one site and you end it at the same site. Okay, this is so-called, this is a local Green's function. And you equate it to the site you singled out. This is mandatory, right? If that is the local Green's function of the lattice, and if this is a description of one of the sites of the lattice, they have to be. Okay? There was a question.
Professor, this second approximation guarantees the translational symmetry?
Which one?
The second one. Yeah, the third one also, right?
Yeah, in a sense, it has to do with it, yeah.
I see. Thank you.
I think it's more self-consistency than translation invariance, because translation invariance is built into everything here. When I put K here and so on.
Yeah, I was wondering because you select a specific site. So
right, but that specific site is not special in any sense.
Oh, I see. Yeah.
No, any site is equal to the other one.
Oh, I see.
Okay?
It's not broken in any symmetry.
That's right. I'm going to break that later, but not at this point. Yes.
So let me ask you
break
something.
That later.
You're interested in the Green's function because looking at the definition, it has to do with somehow with the Fourier transform of the I forgot.
Forget about the Fourier transform. Fourier transform is trivial.
Okay. You're in frequency space somehow.
Yeah.
You can go there, and there's a measurable quantity that is related to that correlation function over there. So that's why you are interested in the Green's function.
No, that's not.
That's not?
No. I'm interested in because, as I said, the only processes I'm going to take into account are processes where you create an electron at a site or destroy an electron at a site as time goes by. These are called single particle processes. Processes where you destroy and create and you do nothing else. There's no two-particle correlations. In other words, spin-spin correlation or charge-charge correlations. These are out. These are not described by the MFT. Okay, I'm focusing on single particle properties. And single particle properties are described by the single particle Green's function. So physically, that's why. The rest is sort of almost obvious.
No, okay, but I'm actually, for now, I'd like to come back to the Anderson model.
Okay.
So for that model, that Green's function is important because it can somehow be connected to some measurable quantity.
Yeah, but you see, I chose the measurable quantity that was convenient for me.
Okay.
There are other
Oh,
measurable
no, of
quantities.
course. But I'm just trying to articulate a question regarding the Anderson model and not the
Okay.
the second model,
Go on.
the dynamical mean field theory.
Okay, go on.
Now. And my question is, you want to look at some material which can be represented by an Anderson model, can be described by an Anderson model, but there's a finite concentration of impurities, but they are very far apart so that you can treat them as isolated.
Yes.
And that's why it's interesting to calculate something related to the impurity, because if you have a finite density, then you can connect your calculations and verify your calculations if your calculations produce that measurable quantity somehow, that measurable quantity that you chose. But now you're using that as a device, as an artifact to treat the really tough problem.
The dense problem.
That you have all sites equivalent.
That's right.
But once you focus on a single site, you can look at it as if that was a single impurity problem from a, let's say, practical point of view in order to implement your approximation.
Yeah, that's completely ignoring the history of things. Because that's not how it happened. But this is how I want to present it to you.
Yeah, of course.
Okay?
History is not important.
Well, it kind of is.
For what you're doing now.
Yeah.
But that's...
Yeah, for what I'm doing now, it's that. But I think the most important physical ingredient is that I'm focusing on single particle processes, in other words, creating and destroying d electrons. And I'm forgetting about two particle processes which are left out of this description.
But that's how mean field works.
The rest is sort of natural.
Okay, but that's how mean field works. You focus on a single site and you treat the
That's right, but there are other mean field theories. There are extensions of the MFT that take into account two particle processes. I'm not going to do that here, okay? Okay, so I just need to write this down. So what is this here? Okay, so let me quickly write it here. If I had this is sum over k e to the I k g of k, in general. Okay, you can put the omega, the t, doesn't matter. As far as the spatial Fourier transform does, this is it. Now, if you make this guy equal to this, or 0, you get sum over k of g c k of omega. In other words, this sum here is what I call the local Green's function. Okay, so writing it here now, this is 1 over omega minus, and I made this equal to the other one, and on the left-hand side, I put the GD. So it's 1 over omega. Look, epsilon d is 0, right? There's no epsilon d here. Okay, so forget about epsilon d. This is my self-consistency condition, okay? Now, let me just do something I should have done, which is the following. This guy was calculated for a given delta. So it is a function of delta. I should actually write this as something like this, okay? It depends on delta. Change delta, change self-energy. And this guy appears again here. So I should really write it like this. Now it's a mess, of course. Why do I do this? Because now, once I write it like this, and remember, my sigma is a black box. A black box such that you give me delta, I give you sigma. I don't care how you calculate it. It's a black box. So if I put it here, and you look at this expression, this is clearly a self-consistency condition for delta. In other words, this is an equation that in principle you can solve and find the self-consistent delta.
Eduardo?
Yes.
I think I got confused about notation maybe.
Probably.
You have DC of 0, right? That's the wave vector 0, right?
No, let's see.
Because you had K
I'm a
before.
physicist, so I call Fourier transform and the original function with the same name.
Oh, this is spatial. That's not, because you are using K above.
Yes.
Now it makes sense.
Yeah,
now it makes plenty of sense. Okay.
Now you're like me, right? You don't change the name of a function when you do
Of course.
So, okay.
Yeah.
Good. So this is a self-consistency condition for delta, okay? Oh, yeah, sorry.
I have maybe a naive question. You're assuming that your lattice is infinite, or this procedure would work if you have finite lattices?
Well, the way it's written here is for an infinite system, yes.
Infinite, yeah. But for a finite system, you can have like an analog for this, because
Well, you
certainly
see, I don't need that, right? I can't do the infinite system with the MFT.
Okay.
Because all I have to solve is the impurity model, which was there, right? I have to solve that problem there. Okay?
Okay.
And that problem, once you write it in terms of the hybridization function, you get rid of the conduction electrons. It's a local problem. It's 1 degree of freedom. So it's actually 1 degree of freedom. But this is infinite lattice. So you don't need to worry about finite size effect. In fact, you can write this, right? The K dependence comes only from the dispersion. So if you have the density of states, you can write this guy as an integral over the density of states of the conduction electrons of omega minus epsilon minus. This is an infinite system.
Okay.
Okay?
And
Later on, when I'm going to talk about extensions to include disorder, then I'm going to have to do finite systems. But here, it's actually has no finite size problems.
yeah, and it's worth, even if you have 1D, 2D, or
Yeah,
three-dimensional system.
as any mean field theory, it's insensitive to dimensions.
Okay.
Okay? So as long as you put the right density, density of states here, it doesn't know which dimensions you're actually working on, which is a weakness of the approach, evidently. Right? Because the dimension 1, 2, and 3 are not the same.
Thank
But
you.
within the MFT, they are sort of irrelevant. Okay? Good. So the algorithm is sort of obvious. You start with the delta, take your impurity solver and find G, take the Fourier transform, obtain GD of omega. From GD of omega, you get sigma. So this steps 2, 3, and 4 are the impurity solver. Now you plug that into the lattice Green function and calculate the left-hand side, which is the local Green's function. Do the integral over K, or density of states. Now you can invert the left-hand side and obtain a new delta in a self-consistency loop, which I call delta nu. If it's the same as the initial one, you've reached self-consistency. If not, you do it again, and you hope it converges. It does converge very quickly for most problems. Okay? That's the approach. Let's see how well it does. Okay? So I can do what you said, right? I can look at the spectral function, but now it's the spectral function of the lattice. Okay? So actually, let me start on the right-hand side here. This is what the theory predicts, okay? This is sort of a cartoon picture. There are papers that calculated this, but this is so nice, I decided to use this. So the local spectral function or local density of states, basically you're calculating imaginary part of this, or with this approximation, right? So what's plotted there is the -1 over pi imaginary part of let's put it GD of omega, because GD is the same as G local at self-consistency. And what do you see there? Well, for u equal to 0, you have a band, a half-filled band, because I want to look at the metal-insulator transition. So you get the band filled to half, a metal. Now you start cranking up u. What do you notice? Well, you deform the density of states. And if you look at this picture here, the picture C, you clearly see 3 bumps. 2 bumps over here and over there. If you look at it, it's u over 2 and minus u over 2. And a bump in the middle. Have you seen that before? That's the same as the Kondo problem, or of the Anderson impurity problem that I showed before. Okay? But as you keep increasing u, it reaches a point where this bump in the middle goes away. And a gap opens up in the spectrum. This is the Mott insulator. So this is the Mott insulator transition according to the MFT, at 0 temperature in this case. Okay? Notice one thing that's very important. When I talked about the single impurity Anderson model, remember that I said that the Kondo resonance, which would be this guy here, the width is given by Tk, right? And Tk is never 0 in the single impurity model. It can be very, very, very small, but never 0. Here, it goes to 0. Why? Because of self-consistency. Because it's not just a single impurity model. It's a single impurity model plus a self-consistency condition. And it's because of self-consistency that you are able to kill the Kondo resonance and go through a metal-insulator transition. Okay? Now, you can look our favorite guest, V2O3, that goes through a metal-insulator transition. And these are measurements and the calculation of the spectral function for negative, this is photoemission spectra, so this is negative frequencies for V2O3. And you see the 3-peak structure. You see the Hubbard, so-called, this is called the Hubbard band. Okay, the bumps on the sides are called the Hubbard, upper Hubbard band and lower Hubbard band. And the quasi-particle peak in the middle, which in the language of the impurity model, I call it a Kondo resonance. But in the lattice system, this is better called the quasi-particle system. These are the metallic quasi-particles of your strongly correlated map. Okay?
Eduardo,
yes, please.
In your cartoon there, you're writing u over omega, and this seems to be like a notation between these two terms of the Hamiltonian, right?
So omega there, no, yeah. Omega there, it's written in the notes, is twice the bandwidth.
It's twice the what?
The bandwidth.
Okay.
I usually use D for the bandwidth. The half bandwidth is D, okay. So this is the bandwidth. Okay. And for a given dispersion, for instance, in 3D, this is like 8T. D in 3D is like 8T. So you can relate
there's a relationship between these two.
Sure. It's very important, of course. You know, the physics depends on the ratio of this to that, and that's the ratio.
Yeah, right.
Yes. Okay, so it does reasonably well. I forgot to mention also that I said that I'm not going to derive this. I'm just going to use physical intuition. But historically now, this was first derived by looking at the infinite dimensional limit of the Hubbard lattice. So if you look at this in infinite dimensions, you basically derive everything that I wrote here. Okay? Which is also not surprising because one of the ways of deriving mean field theory, as you know, is by appealing to infinite dimensions. Okay? The way it was done was through Feynman diagrams. Very non-transparent way of looking at it. This picture that I showed you here, which is the picture of the MFT as an impurity problem plus a self-consistency condition came later. Okay? But it's the one that everybody uses today because it's much more physical. It's much, because you can appeal to your knowledge of the single impurity problem, for instance, Hubbard bands, Kondo resonance, and so on, to understand what's going on. Okay? Let's see other results. You can find the finite temperature phase diagram of the model. If you do that, this is the theory. You have a first-order transition ending at a critical point. Very much like the first-order transition ending at a critical point of V2O3 that I showed before. There's an antiferromagnetic phase at low temperatures because, as I said last time, at low temperatures, the Hubbard model at half filling for strong coupling maps onto a Heisenberg, an antiferromagnetic Heisenberg model, so it's no surprise. So DMFT can be also generalized to account for antiferromagnetism. I'm not going to go into that, but it can be done. You define self-energies for two sublattices, for spin up and spin down, and so on. You can describe the antiferromagnetic phase. It's not a very good description of antiferromagnetism because antiferromagnetism is spin-spin interaction, which is more than single particle process. But it's there, okay? So the important point is that it has a first-order line and the anticritical point. As any first-order line, it has hysteresis, and you can define two curves that flank the first-order transition line, and these are called spinodal lines, or UC1 and UC2, as you see there. And what that means is that you can supercool or superheat, between quotation marks, because this is U, right? So you can increase or decrease U. And for instance, if you come from the metal, from a liquid, and you increase U, you can cross the first order line and still be metallic on the other side at a metastable state in this region between the dashed line and the continuous line. Likewise, you can go from the insulator, decrease U, and still be insulating across the first order line because you are at a metastable point. The transition line is the dashed line here. This is like any other phase transition, first order phase. Not every first order phase transition, but many of them are like that. Okay.
So UC1 is a metallic antiferromagnet, and UC2 is an insulating ferromagnet?
No, UC1 and UC2 are spinodal lines. These are...
Okay, sorry. I meant the ordered phases.
Well, UC2 gives you the largest value of U you can go and still be metallic. And UC1 is the lowest U.
No, but I meant deep in the red regions.
Oh, no, the red region you are...
In the ordered phase?
Yeah, we wouldn't know if it's metallic or insulated.
Yeah. I mean, the ordered phase is metallic.
One side is metallic, the other side is
small
insulated.
U, and the other is insulated and antiferromagnet.
Yes. Because what determines there is whether you close the gap or not. That's what determines. There's an interesting thing here, which is as liquid-gas transition, it can go above the line, above the critical point, and you can go from one side to the other continuously, right? And if you do that, you are in this region, which is usually called a bad metal or a bad insulator region, okay? Because it's neither a good metal nor a good insulator, okay? Remember that you can only rigorously tell if a system is metallic or insulator at 0 temperature. Because then one is infinite resistivity, the other one is 0 or finite resistivity. At finite temperatures, both insulators and metals have finite resistivity. There's no symmetry breaking across this transition. That's why you can go over it. And you cross that region there where you have a bad insulator and a bad metal, and you can do calculations there of the resistivity using the MFT as a function of temperature. And you see you have these two famous fan-like lines. So lines over there, you're going insulating as you go to low temperatures. below the separatrix there, you go metallic. And you can actually scale those lines onto two branches of universal lines as you approach the critical point. Okay? And this is seen in many experiments by now. These are organic two-dimensional compounds that have a metal insulated transition, and this fan-like behavior is seen everywhere. Okay? So it does quite good. It's very good at higher temperatures where you're not interested in antiferromagnetism and so on, which is where you can actually really define a Mott transition. Because usually you have antiferromagnetism at low temperatures. Unless the system is very frustrated, then you kill antiferromagnetism and you have this huge Mott transition. But usually you order. Right? But what we call Mott transition is what happens at that first order line above the antiferromagnetic phase. Okay? Okay, so now I want to put this order. So what I want to do is to adapt this approach to a disordered system. So what kind of disordered system? Well, you can take the Hubbard model again, and you add a disordered term. So if you have impurities in the model, you can add a term that has sort of this is not the only way of adding disorder to the model, but it's certainly one of them. You can add a random on-site energy in your system. And you can ask, what does the MFT do for us in this case? Okay?
Random on site?
Yes, random on site.
It looks like a hopping.
Oh, this is because I made a mistake.
Okay.
There's a typo right there. There's an N there.
The N there should be I.
N should be
Yes.
I, okay.
The N there should be I. I'm sorry. Okay? So what can I do now? Now, once again, you can derive what I'm going to tell you by appealing to the infinite dimension limit. I'm not going to do that. I'm going to appeal to your physical intuition. Okay? Okay, so now, how do I modify everything here to deal with the disordered term there? Okay, first thing, that's the problem I want to solve. First thing is I fix this. Okay? So this you keep. So I'm going to use, I don't know, these you keep. It's very important. One hybridization function for all the sites. What does this mean? It's some kind of average. Precisely what average I'm going to tell you later, but it's some kind of average. Okay? So this is the MFT for a disordered system. Let me see where I am here. Okay, so I keep, first step, take a certain delta for every site. Now I solve the impurity problem for every site, but now every site has a different energy, right? So now I have to put epsilon I here because every site is different from the other. In other words, this guy now should be GD, let me put epsilon I of omega. Let me put the dependence inside the notation here, because this is like the epsilon D of the impurity model. So for every site, I have a different epsilon D, right, because of that term there. But then you solve the problem for a given unique hybridization. Well, this is going to be different too, right? For a different epsilon D, you have a different self-energy. So the self-energy is going to vary in your lattice, depending on the site you are. So this is why I wrote it here like that. This is sort of the best attempt at the schematic representation of disordered DMFT. Okay, so you solve the impurity model, and you find this. And you find this. Now I have to make contact with the lattice, okay? I have to impose self-consistency. How do I do that? Well, first of all, now things are a little bit different now. It's the same spirit, but different. How do I do this? I think I can do it here. From the local Green's function here, I can obtain an average Green's function. So let me write it like this. So over bar for me is this order average, okay? So the average Green's function is going to be the epsilon, P of epsilon. This is the distribution of the epsilons over there. Omega minus epsilon I minus delta minus, well, okay, I can find these guys. I have my all-powerful impurity solver, so I can find this, and then I can calculate this average. And then I do the following. I think I have to get rid of stuff here now. Yeah, I'm going to get rid of this part here. Well, this is...
Eduardo?
Yes.
Should there be an I in the epsilon in the denominator of the integer?
Yeah, no.
Okay.
No, because it's integrated over here. Sorry.
Because this guy pointed that out.
Thank you. Okay? Now, what I do is the following. I define a sort of an effective self-energy. This is the following. I'm not going to write delta here because of lack of space. But of course, this is dependent on delta. And this is going to be defined as 1 over omega minus this minus effective self-energy, which I call sigma EM. EM for effective medium. What I'm doing here is I'm saying that the average of the medium of the disordered lattice is such that you can define sort of an average self-energy or an effective medium self-energy through this equality here. Because now I'm going to say that this is going to be the self-energy of the conduction electrons. And then I can impose self-consistency. Okay? You see, I have to do this because there are many self-energies now. So I don't know what to do here now with the conduction electrons. So I define a sort of an average, effective medium self-energy this way, and plug that into the conduction electrons and impose self-consistency. And that's the problem again. Okay? Once again, if this looks sort of arbitrary to you, this comes from the infinite dimensional treatment of the problem.
So
yes?
If you're performing some kind of an average, there shouldn't be
the Anderson transition.
Shouldn't there be a sum over I on the left-hand side?
Of what? This?
Yes.
The sum over I is here. It's not a sum over I. It's an average over I.
Okay. Because sigma is already
right. Every side has its own energy and its own self-energy. Every side is different from side to side. Okay. I put them all here and take an average. From that, I define the effective self-energy, which I put into the conduction electrons Green's function. So I'm going to sort of skip all this stuff here, because now you are experts on this. So what I'm going to say now is that
No, sorry, I still don't get it. You have to have an expression for sigma on the this one, no, that one on the left-hand side. You have to have an expression for sigma as a function of epsilon.
which sigma? There are two sigmas.
The sigma on the left-hand side.
Yes.
You have to have an expression for this
Yes.
as a function of epsilon.
In other words, you have to solve many impurity problems.
Of course.
Right?
Of course. So that you can integrate over epsilon.
That's right.
Okay. Okay, so, okay,
Okay.
fine.
So let's do a more modest calculation. Binary disorder, right? So epsilon can take on two values, plus delta and minus delta. Okay? So you have the distribution is a delta function at plus delta, delta function at minus delta with a half probability in each one. So this is going to be two terms, half plus delta, plus half minus delta, minus delta. This is the simplest binary alloy case of disorder. But you can do many things. You can do integrals and so on. Okay?
P now distribution of...
Distribution over there.
Okay,
P is there.
okay.
P is there.
No, it's not rho, because I was thinking that it was...
No,
rho,
yeah, I
rho,
know.
but-
I know.
Okay, but
which is why I'm writing it differently. So this is now the conduction electron self-energy. The local one is, of course, sum over K, 1 over omega minus epsilon K minus the medium. And we equate this to and you have self-consistency. So I think I have the loop here. Let me see. Yeah, there's the loop again. Start with a given delta, find all the Green's functions, the different ones. From them, find all the, it's not there. Oh, well, it's not over there. It's not there, but find all the sigmas, okay? Then you do the average. The average is here, from which you get sigma effective medium. Plug that into the conduction electron Green's function, calculate it, and equate the two. And this is a self-consistency condition for delta. Everything is every guy here is a functional of delta. Delta is a function, right? This is also a functional of delta. So, so this is a self-consistency condition for delta, okay? Once again, this comes from infinite dimensions if you want to derive this, but can also be sort of physically motivated, as I have done here. Now, a few comments are important here. Let me see if there's something else I have to say. Yeah, the most important comment is the following. First of all, if disorder goes to 0, you recover the MFT. That's obvious, right? Disorder goes to 0. This is a delta function. There's only one self-energy. This guy is equal to that one self-energy, and you recover the MFT. Same thing. But there's another important limit, which is the U equal to 0 limit, right? The non-interacting limit. Still a disordered problem. A disordered problem is still difficult. So what does the MFT do for the non-interacting disordered problem? Okay, for those of you who know, this is completely equivalent to an approximation for disordered systems called the coherent potential approximation, or CPA. So if interactions are 0, this is CPA treatment of disorder. Okay? Now, CPA, I don't know if anybody here has ever worked with CPA. CPA is very good, but it does not have a very important ingredient. It does not have Anderson localization. I'm going to talk about this tomorrow, but a non-interacting system of particles, quantum particles, either bosons or fermions, doesn't matter, because it's not interacting. So I'm talking about the spectra. is such that if the disorder is large enough, states which are usually at low disorder, delocalized over the whole lattice, they become localized. They only occupy a certain region of space. This is a very important phenomenon called Anderson localization. I'm going to talk about this tomorrow. So CPA does not describe Anderson localization. Therefore, DMFT plus disorder also does not describe Anderson localization. So it has its limitations. Okay? If the disorder is not too large, however, CPA is an excellent approximation. Okay? If you know what you're doing, you can work with CPA with good results. But if you're reaching the limit of Anderson localization, you also should know that you're not doing a good job. Okay? So this is the MFT for interactions plus disorder. Let's look at some results. So the disordered Mott transition. So in other words, the Mott transition of this model with the added disorder term. What does disorder do to the picture I showed before of the Mott transition of the Hubbard model? So here are two phase diagrams. This is at t equal to 0. This is at t different from 0. So let's first look at t equal to 0. Forget about these lines here, these dashed or dotted lines. Just look at the full line. The full line separates the Mott insulator from the metal as a function of disorder. W now is disorder. Okay? W here is disorder. So you are increasing disorder, dividing everything by U, and you have that. So what happens when you increase disorder? You kill the Mott transition. The Mott transition line goes to 0. That's very easy to understand because what does disorder do? It creates states within the gap. Anybody that has ever studied semiconductors knows that if you add impurities to a semiconductor, one of the things they do is to create impurity states within the gap, within the semiconducting gap. Okay, so here's not different. You create states within the gap, so you start filling up the gap, and eventually you just destroy the Mott insulator. This is not very exciting. Okay? At finite temperatures, you remember that these are the two spinodal lines. The phase transition line is not there. These are the spinodals, the UC1 and the UC2. As you increase disorder from 0, so the black dashed lines are the spinodals for this, okay? UC1 and UC2. This is the black line. And then you start increasing disorder, and what happens? You suppress the transition, so TC goes down. TC is the point where the two spinodals meet. So TC goes down, and it also shrinks the region between the spinodals, which is called the coexistence region. Yes?
When you added disorder in your model, you just showed us that there is a distribution P of epsilon, and you did not comment anything about that.
Right.
And now you are showing us that disorder, of course, matters, and then, it depends on that to the phase. My question is, are you assuming that the distribution of disorder is not important? Depending on the distribution?
Yes, in a sense I am. It's not completely true, but most disorder distributions that you take, and usually you take, there are, usually 3 possibilities: uniform, Gaussian, or bimodal.
You have a power law.
But that's much harder to get in real systems. Actually, I don't know how to get it. I'm going to talk about power laws later, but they're not natural in the microscopic system. Okay? No, but there's more to that, because there is certainly, for instance, in semiconductors, the disorder is much more in the hopping term than in the epsilon term. Okay, so
yes.
These questions do matter. Yeah. I'm brushing over them.
You are assuming that you have the finite
probably,
average of your disorder.
Yeah, this is probably uniform disorder. I have to look it up, but it's probably uniform disorder. Okay, so this is not too surprising, I would say. Okay, but this is more interesting. Okay, So I think, oh, okay. So let's look at the left-hand side here at t equal to 0. So what does this, what is this plot here? The plot there is the scattering rate as a function of u for different levels of disorder. So disorder is actually going up here, but you're plotting as a function of u, and that's 1 over tau. What is 1 over tau? 1 over tau of u is twice the imaginary part of this effective medium self-energy at 0 frequency. Why do I plot this? Because if you do a resistivity calculation, this is what goes into the resistivity. This is what determines the resistivity of your system. So if this is large, it means you have a very dirty system. This is at t equal to 0. At t equals to 0, there are no, as we call it, inelastic processes. In other words, there are no electron-electron interactions where one electron comes and loses some energy to the other one. Because you're at t equal to 0. This is ground state property. But there is disorder. Disorder sort of messes up your system, and the resistivity, which for the metal should be 0 or very small, it's going to be finite. So this is a measure. This is, in a sense, this is a resistivity plot. Okay? And what you see here is that no matter what the disorder is, the resistivity goes down in interactions. This is a little bit surprising. What's going on here? This has to do with pinning. Remember I told you that the pinning effect basically brings the Kondo resonance to the Fermi level always, no matter where you put the epsilons. So in other words, if you look at this guy here, at the Fermi liquid regime, at 0 frequency, let's say. Well, let's leave it here. In the Fermi liquid regime, this is going to be approximately given by omega minus, now here I have epsilon I have delta 0, and I have what I call small delta. That comes from the Fermi liquid part. And then here you have minus z delta plus delta 2. Okay? At 0 temperature. This is the Fermi liquid description. Now, pinning means that this guy is almost 0. Remember I talked about pinning, right? But see, this is the disorder that you put in your system. What these two guys are doing, especially this one, which is due to interactions, is adjusting its value so that this sum is 0. In other words, you're sort of screening the disorder by interactions. You are decreasing the effect of disorder through the pinning effect of the Kondo problem. The effective disorder is screened down to basically 0, right? It becomes very, very small. Okay, so this goes into this. You can calculate the average, and this will give you this, and this will give you that. But if this is very small, the imaginary part is going to be very small. This is why there is screening of interactions, as you see there. So this is a very non-trivial effect, comes out of the DMFT, comes out of interactions. It's an interplay between interactions and disorder. Okay? This is even more interesting. This is the spectral function, basically the imaginary part of this guy, as a function of frequency. But look, first of all, this panel A, for two different values of interactions, panel A is the average spectral function. In other words, it's the imaginary part of this thing. Okay? It has some form there. Now, the interesting thing is the following. This is the fluctuations of that quantity. Okay, so it's the relative fluctuations of that quantity. In other words, if disorder is 0, this is 0. This is only different from 0 because of fluctuations induced by disorder. And what do you see? The relative fluctuations are extremely small at low energies, but they are large at large energies. So this is, again, spinning, low energies. This is screening disorder, suppressing disorder by interactions through the pinning effect. But it's not effective at large energies. At large energies, this does not work. This is a property of the Fermi-liquid regime, which is low temperatures, low energies. Okay, at high energies, the fluctuations are huge. This is where the Hubbard bands are. There, you cannot control what disorder does. It fluctuates crazily, okay? So at low energies, there's effective disorder screening. At high energy, there's nothing, okay? And this comes out from the interplay of disorder and interactions, okay? And of course, I covered much less than I planned to. I don't know. What should I do? Maybe I can go through this quickly. I don't know. One other interesting thing you can do with this, with the MFT plus disorder, is to analyze the so-called Anderson lattice model. This is no longer the single impurity model. Now I have one impurity site for every lattice site. Okay, so the F, I changed notation from D to F, because usually these are F shell elements, rare earths and actinides. And there's one, there should be a summation of I here. Many mistakes, right? So this should be a summation of I, because there's one F orbital per lattice site. There's one C orbital and one F orbital per site. Okay? So this is a dense lattice of impurities. I start with a few impurities, but then I put more and more. Eventually, I form a dense stoichiometric lattice of magnetic impurities. And this is so-called Anderson lattice model for obvious reasons, because you took the single impurity model and you created a lattice out of it. And this is my best attempt at a picture for this guy. So the blue spins here are the F electrons, and the red ones are the conduction electrons going around. Okay? And this is an important model for a very large class of materials called heavy fermion materials. And you can use the MFT to analyze this model. So let's quickly look at what happens here. If you put disorder in this model, you can put disorder in many places. You can put disorder in the conduction electron band. You can put disorder in the F sites, in the hybridization sites. You can even put disorder on the U's if you put different types of magnetic atoms. Okay? And then you can do the MFT calculation. I'm not going to go into any detail about it, but it's basically the same that I did here, not very different. Except that now, as I said, at each site, there is a C and an F, and the C is the one that sees the average hybridization, the unique average hybridization. So this is my picture for that. So this is fixed, but these guys vary from site to site. Okay? So now, I talked about pinning, but the other important, actually, this is wrong, right? I should put an I here because this is also I-dependent. The other important aspect of the spectral function is the Kondo temperature, or the quasi-particle weight, the width of the resonance. That's related to this Z here. In other words, Z times the imaginary part of delta is what I call the Kondo temperature. Now, if it's a disordered system, the Kondo temperature is going to fluctuate, right? So I can write the Kondo temperature now as site-dependent, TKI, and everything that goes into the exponential here can depend on the site, right? The V, the EF, even the conduction electron density of states that can be affected by that term. So everything there can fluctuate, okay? Yes?
Professor, in the other case, in the Hubbard model, this...
They are distributed too.
Yeah, the screening is about charge, right? Just to make sure.
No.
It's also
no, this is Kondo effect. It's not charge, it's a spin.
Oh, I see.
Yeah.
Because it could be Kondo effect with effective charge, but yeah, it's a spin.
It's a spin. It's a spin. Okay?
Thank you.
So, in other words, because of disorder, the DMFT treatment of this problem will have a distribution of Z's and therefore a distribution of condo temperatures, right? Which is here. Now, the nice thing about this is the following. These quantities here, which fluctuate, go inside an exponential. So even if the disorder of these guys is small, the disorder in TK can be huge because of the exponential dependence. And this is actually what happens. So you can ask about some properties of this problem. For instance, you can ask about the spin susceptibility of the system. Now, of course, you're going to say, oh, it's very hard to calculate the spin susceptibility of this complicated system. However, we know that you can actually prove it within the MFT that spin susceptibility is actually additive. In other words, you can add the contribution of the different sites and get the full spin susceptibility. This is an excellent approximation for the full spin susceptibility of the problem. Well, if that's the case, then you can take as the distribution of condo temperatures of your problem and calculate the full susceptibility by averaging over the condo susceptibility, which is this expression here, which is plotted over there. It depends on, remember, it depends on TK and T. Actually, it's a universal function of TK and T, remember? We talked about this in the first lecture. And you can average it with the given TK distribution of your problem, which can be very large. So the result of this calculation for, this was sort of an experimental theoretical collaboration. So some guys who did NMR and spin susceptibility of this system, they came up with the distribution of the guy that's inside this. Actually, this is what they call lambda, right? This rho F times JK, they called lambda. And they could sort of fit their experiments, their NMR experiments, to a distribution of these lambdas. And from the distribution of the lambdas, you can get the distribution of TK. And look at this. The distribution here is actually extremely narrow. If you calculate the relative fluctuations of lambda, it's like 0.2. It's very small. But the distribution of TK that comes out of this is this one. It's very large. It's very broad because of the exponential dependence. And most importantly, it sort of goes to a constant as TK goes to 0. This has huge impact on the results. Now, since I'm running out of time, I'm not going to be able to show this, but as long as if you have the condo susceptibility and you average it with the distribution of condo temperatures that goes to a constant as TK goes to 0, the result you get is a log behavior. So you get something that goes like log of lambda over t as t goes to 0. And this is what that curve shows. This is the susceptibility for different values of the applied magnetic field. So the upper one is the smallest magnetic field. So that's the one you should look at. And it's a log dependence. Okay? This is extremely non-trivial. It's very hard to get a log divergent susceptibility. This is what we call a non-Fermi liquid behavior, because the susceptibility of a Fermi liquid is a constant, goes to a constant. But this diverges logarithmically. The same thing goes for the C over T, so specific heat divided by T. And it comes naturally out of the disorder treatment, the DMFT disorder treatment of this problem. Now, the other thing that can be done is look at the resistivity. The resistivity is not additive. It's not as trivial. It's more complicated. And I'm just going to give you the result. If you do the average over TK, you get this linear resistivity. You get actually a finite intercept and a negative linear behavior with temperature, which is also non-Fermi liquid. Fermi liquid is T squared, something like this, a power greater than 1. This is also non-Fermi liquid. It comes out of this disorder. This came to be known as condo disorder for these systems, okay? And this is a very nice result that comes out of the MFT, and is extremely non-trivial because, just because of the exponential dependence of the condo temperature. And so it sort of amplifies hugely the disorder of the system. So it's, pinning sort of suppresses the disorder. But if you look at the condo temperature, there is a huge enhancement of disorder due to also strong correlation effects, okay? So I think that's the last thing, yeah. The other thing I wanted to talk about, you can look in the notes, it's quasi-crystals. You can, actually in quasi-crystals, you can calculate distributions of condo temperatures, and there are power laws. Maybe I'll tell you next time, but anyway, thank you. Sorry it took me so long.
Questions?
There's one here, closer to you.
Thanks. So this is a very, very general question, so I left it to the end. You have this first order transition and the spin nodals on the left, on the right. So it's a transition driven by temperature or energy, I don't remember.
It's you, the interaction.
It's you. So we know from equilibrium phase transitions, no? That when you have the first order transition, typically you can have, for example, a overcooled liquid, and then it's still liquid while it should be solid.
That's what I said.
And then, yes.
Okay,
but what I didn't catch is that, so how do we, physically, what is happening with the thing that is undercooled? So it's still conducting when it shouldn't conduct anymore? How is that nucleation of an isolator appears and grows? Can you elaborate a bit conceptually on that?
Well, first of all, it's as you said, it's a function of U, right? So what is U if you are an experimentalist? It's pressure, basically pressure. You can, not U, T. You tune T with pressure, and U over T, of course, is what you need. So if you apply pressure, you can go through the transition in V2O3. I showed it last time. And it do have hysteresis there, and you do have, maybe I can try to find it here. Oh, no. This is the best plot for that. Okay, so this is the first order transition with hysteresis. You go, this is pressure. So you go down, if you come from high pressure down, you go down along this curve, but if you go back, you go up on a different curve, right? So whether you are reaching the spinodal there, I don't know, but you're certainly, you don't see one jump only, you see two. So you're supercooling and superheating, there's no doubt about it. Whether you're reaching the spinodal line, I don't know, but this is clearly superheating and supercooling.
So, but eventually, the nucleation of the low P phase, for example, we should understand it as a piece of the material that eventually compress a little bit more or dilate a little bit more, and it stops being, okay.
Yeah, and nucleates.
It goes. Okay.
Yeah. Okay. Although I'm not sure that's have...
or is more electronic thing?
No, it's completely electronic. It's completely electronic.
Yeah, okay. So it's an electronic cloud that is more or less compressed then.
Yeah, it's compressed, but, well.
Okay.
One thing is theory, the other thing is experiments. So when we look at this, we think of it as completely electronic, and the only thing that pressure is doing is changing U over T. Okay. That's a theorist picture. What happens in nature, of course, is a different story. You're compressing the material. I'm pretty sure it's going to have a coupling between electronic and lattice degrees of freedom. There's going to be some disorder there. Disorder is going to nucleate stuff. So real life is tough. It's complicated. What I find amazing is that still you see the stuff there, right? But I'm pretty sure. Now, you can ask whether people have experimentally tried to look into that question. Yeah. There are some experiments, I don't have plots here, where they look at, for instance, the local conductivity, something they call near-infrared spectroscopy. They come with a probe, and you can locally measure the conductivity. And you see a landscape of conductivities, and they do it in V2O3, but they did it first for VO2, which also has a metal insulator transition, which is strongly coupled to the lattice, VO2. And there is disorder, but you see puddles of metals and puddles of insulators there. But then they do it to V2O3, which we believe is not so much coupled to the lattice, and they also see the puddles there. And then there is disorder and so on. And it's beautiful experiments. You can see the sizes of the... And we actually calculated this with the MFT. At finite temperature, you see these bubbles of metals and bubbles of insulators and so on. And for instance, for the statistical physics buffs here, the disordered model is it's a random fieldizing model. So the transition is an Ising transition. The disordered is a random field.
Some people would say that everything is a random field Ising model.
No, but yeah, okay. Anyway, so because the disorder couples to the density, and the density is sort of the Ising or the parameter. And anyway, so in 2D there's no transition. It's also there's glasses. Yep.
Yeah. So you in the DMFT or the CPA you rely on the single site approximation, right? And I have two questions. One is how do you go beyond this single site approximation?
Next time.
That's next time.
Yeah. Well, no.
Next lecture.
No. Let me rephrase that. There are two things about your question. It's not really single site. I prefer to call it local.
Yeah.
Because what matters most to us is how you treat interactions. So the treatment of interactions is local in the sense that there's no K here, right?
Yeah.
This is a local treatment of interactions. As far as the disorder goes, it's CPA. Within the MFT is CPA.
Yeah.
Now, you can ask how you go beyond that.
Yeah.
How you go beyond CPA, I'm going to talk about tomorrow. And an extension of this theory that does have Anderson transition. You have to go beyond CPA.
That was my second question. What's missing in CPA that it doesn't capture the Anderson transition?
I'm going to be more specific tomorrow, but the most important thing is Anderson localization. And that, we can go beyond that. To go beyond the local treatment of interactions is much harder, much harder. It can be done. It's not as nice, I would say. Anyway, you can go beyond. It's much harder. Huh?
We'll see it tomorrow.
Not this part. The second part, I'm not going to talk about. I'm going to talk about how to go beyond CPA, beyond the treatment of disorder, which here is CPA.
Mm-hmm.
So tomorrow, no CPA. But local, go beyond local in interactions. See, tomorrow I'll still be local. I'll go beyond CPA, but local. I go beyond local, it's a much harder problem.
Okay, thank you.
I have a question which I think is perhaps related to what Ezekiel was asking, because everything you showed us, at least, I think is a cartoon, but it was in a square lattice.
Mm-hmm.
And it comes in the first summation of your Hamiltonian there, I guess.
Just here, right? If
Okay.
I go to a different lattice, you're going to modify this.
And if you have something disordered there, because you had the disorder everywhere except there, does it change
No, in a sense I did, right? Because the disorder I put was a local term. I added here, like, so this term is like this. It's like a local term of this.
Okay.
But it's just that I treat it separately from this. Okay, so in the sense, this gives rise to the dispersion there, and I treat it as this within CPA.
But the lattice disorder would play the same game as the one that he was showing us as a W there. Would be the same kind of, as if you would use a delta.
You mean the bandwidth?
Yeah, in the sense that
yeah, the bandwidth is there.
I mean, because it's a different type of a disorder, no? Than the one that you were adding through the distribution of A.
That was not disorder. That was just the bandwidth. Maybe I'm confusing.
I'm just saying, you are treating disorder. You said, well, disorder plays an important role because you are populating, you know, the band gap, and then you
Right.
can destroy the...
That's right.
But then the question is, what happens if you add, let's say, instead of an ordered lattice, you could have the same type of...
Yeah, but what does that mean in terms of the Hamiltonian? You can put disorder here. Yes, you can do that.
Right.
You can do that. That's off-diagonal disorder. You can do it, you can generalize it, you can treat it. Usually it doesn't matter too much. There are a few problems where disorder in this is very different from disorder in this, but usually they are sort of similar, okay?
Hi. Can you add spin orbiter coupling term in your DFMT?
Yeah, absolutely.
If so, how does it change your whole approach?
Well, if you're talking about the local spin orbit interaction, which usually it is, right, a local term,
Yes.
it's very easy because it's a local approach. Everything that you do locally is easy to do here because, in other words,
but I thought like, how does it change the whole microscopic quantities with the addition of this spin orbit?
What I can tell you is the following. I can mention to you a few systems where this is important and this has been done, okay? So for instance, have more than one band. In other words, more than one orbital per site, and you put a spin-orbit interaction term between them. One of the things that people, you probably, I don't know, there are a few systems that have this kind of physics, and people have introduced disorder in the spin-orbit interaction in their description. I'm not sure I know of a very important effect that comes precisely from spin orbit there. I'm not sure there is one. Maybe there is. I just don't know. But you can put it. Everything that's local is very easy to adapt here. For instance, this is not local, right? This is between sites. So it's not an immediate extension. It can be done. It's not impossible. But it's a different, it's a little bit different. You have to work harder to incorporate here. Unfortunately, I can't tell you more than this. I'm sorry.
Any other questions? So let's thank Eduardo again. And we'll be back here at 2.